Hi, and welcome to our 128th test and measurement video. Today, we'll discuss the two principal processing formats available in digital storage oscilloscopes using this 4-channel Tektronix MDO 3000 series oscilloscope. An electrical waveform can be displayed in either the time domain or the frequency domain, and the oscilloscope can easily switch from one to the other any number of times with no loss of information. To demonstrate, first press Default Setup to disable any previous setups that may interfere. Then, connect the internal arbitrary function generator to one of the analog channel inputs and press AFG. This permits the oscilloscope to display any of the 13 internally generated waveforms. For this demonstration, we'll use the sine wave, which is displayed in the default time domain. Domain is a term used in calculus, and it refers to the independent variable, which is time. I can't imagine a universe where time is the dependent variable. In the time domain, time is plotted against the horizontal x-axis, which is divided into seconds or fractions thereof as appropriate. The dependent variable, amplitude, is plotted along the y-axis, which is divided into volts or millivolts as needed. If we are looking at a current waveform, the y-axis is divided into amps or milliamps. For power, the parameter is expressed in decibels. The whole thing is laid out in accordance with Cartesian coordinates invented by René Descartes in the 17th century. To summarize, the domain graphs the independent variable before the function is applied to it, and the range displays the dependent variable after the function is applied to it. The other principal type of display is known as the frequency domain. To display the same waveform in the frequency domain is very simple. The mathematics is complex, but the oscilloscope does it all for you. Just press Math followed by the soft key associated with the second item in the horizontal menu, FFT, which, as we shall see, stands for Fourier Transform. Now the frequency domain is shown in the same screen along with the time domain, which is what a mixed domain oscilloscope does, and this is very useful in some troubleshooting operations. In the frequency domain, again, we see amplitude plotted against the vertical y-axis, but it is now in units of power rather than volts, and the scale is logarithmic for viewability rather than linear. The irregular fluctuating trace at the bottom is the noise floor, similar to the snow you see on the screen of a TV when it is tuned to a channel that is not active. The sine wave fundamental is concentrated at a single discrete frequency. You may not be able to make it out because it is crammed against the edge of the display. To clarify, move the BNC cable over to the RF port. Press frequency span, and for center frequency, enter 100 kilohertz. That puts the fundamental at the center of the screen. Since it is a sine wave, there is not a series of harmonics. By pressing two buttons, the user can have the oscilloscope instantly shift between domains. But centuries of complex mathematics were required to set the stage for this miracle. Joseph Fourier, 1768 to 1830, was a French mathematician and physicist who, among other things, accompanied Napoleon as scientific advisor during his invasion of Egypt. Returning to France, Fourier formulated what became known as the Fourier Series. In the analytic theory of heat, he published it in 1822 and stated that any function of a variable, whether continuous or discontinuous, can be expanded into a series of sines of multiples of the variable. This work is the foundation for what today is known as the Fourier Transform, which consists of analysis and synthesis of the two domains that we saw in the oscilloscope. What it is saying is that we can go back and forth between one and the other any number of times with no loss of information, limited only by the precision of the instrumentation. Needless to say, Fourier was not at the time thinking of periodic electrical waveforms. His investigations pertain to heat transfer on a molecular level, which he studied in an iron ring. However, his theoretical work has been generalized, becoming applicable to every kind of electrical and chemical reaction that we can imagine, and today it pervades vast realms of classical and quantum physics. In mathematics, underlying the Fourier transform is highly complex, but it was greatly simplified by the rediscovery in 1965 by James Cooley and John Tukey of what came to be known as the fast Fourier transform. That is based on work that can be traced back to an unpublished work of 1805, predating the Fourier transform, by Carl Friedrich Gauss, in which he interpolated the orbits of asteroids Pallas and Juno from simple observations. FFT is an algorithm that computes the discrete transform of a sequence or its inverse. Fourier analysis, as we have seen, converts a signal from its original domain to a representation in the frequency domain. And Fourier synthesis is the reverse part of that transform. Thanks for watching. New videos are added periodically, so check back frequently.